In this video, we're going to talk more about arrays. Specifically, we're going to talk about directivity, Endfire arrays, and 2D planar uniform arrays. First of all, in general, the directivity of an array is kind of hard to calculate exactly in closed form. And that's because you have to evaluate this radiation integral. Where you're integrating over the solid angle of a sphere, sine of nkd over 2 cosine theta, again assuming that the array is along the z direction, divided by sine of kd over 2 cosine theta. That whole quantity squared sine theta d theta d phi. It's kind of a lot to do. It's best to do that numerically. And actually, your textbook comes with a CD that has some tools for evaluating this numerically, or you can just write it up in MATLAB yourself. That's not too hard. But for certain special cases, we can approximate this. So at broadside, which remember, broadside is, if this is my array, broadside would mean that the main beam is pointing this way, so zero phase shift. If we are in the situation where KD is small and N is large, then the maximum directivity of this type of array is approximately 2 ND over lambda, which is equal to 2 times 1 plus the total length divided by the spacing times d over lambda. And you can approximate that one more time. If the length is much greater than the spacing, then that simplifies to the directivity being approximately equal to 2 times the total length of the array in wavelengths. Well, this is kind of interesting if you compare it to the equation for effective aperture. Remember, effective aperture of an antenna of any kind, including an array, is lambda squared over 4 pi times the directivity. In the case of a uniform linear array like we're talking about, if you work out this effective aperture, it turns out to be the length of the array times lambda over 2 pi. So you can think of it as, okay, here's the length, and I guess here's the effective width of the array. So it's sort of giving the array an area, even though it technically doesn't really have an area. So that's for broadside arrays. Remember that broadside arrays have a radiation pattern that is symmetric around the axis of the array. It's a donut shape, and all of the side lobes make little conical donut shapes too. Everything's a donut shape. It's hard to draw that in 3D, so yeah. What if you wanted to have the array so that the beam just points along one direction like this? You can do that. That is called Endfire. Pretty self-explanatory. Endfire is when the main beam is just along the axis of a linear array. There are a couple different ways to realize this. Ordinary Endfire has a progressive phase shift, beta, applied to each element of minus KD if you want the main beam direction to be at 0 degrees, or plus KD if you want the main beam to point at 180 degrees. The directivity of an ordinary Endfire array, again, under the same circumstances where you have a large number of elements and a small spacing, that directivity for Endfire is approximately 4n d over lambda. That's twice the directivity of a broadside array, and that's because the main beam is only pointing along the axis instead of being in a donut shape. And then if you, again, make the further approximation that the length is much greater than the spacing, then that's approximately equal to 4 times L over lambda. There's another type of Endfire array called the Hanson Woodyard Endfire array. The difference between this one and the ordinary Endfire array is best illustrated by going back to a Cartesian plot of the array factor. If we do that, and then we set up the ordinary Endfire array, let's let for this KD equal pi over 2. So remember, this occurs at 2 pi. So pi over 2 is right about here. And then for an ordinary array, beta is KD, or minus KD. We'll make it plus KD because we want it to point this way. So the circle for an ordinary Endfire array is going to be that wide, and it's going to show up right here. If you do this, you end up with a pretty wide main beam because of the way that the circle shape stretches out things that are at its edges. The Hanson Woodyard array shifts the center of the circle by a little bit more. Just shifts it over by a little bit, which means that instead of being right there, it's going to be right here. And the edge of the circle that we draw is also going to be shifted over by a little bit. So doing that, our new polar plot circle, looks about like that. And that means that my 0 now projects down to there. And I get a narrower main beam. The value of beta for a Hanson Woodyard array, the progressive phase shift, is going to be minus KD plus pi over n. And that's just by cutting off a small amount of the main beam. We narrow the main beam, and then we increase the directivity. We're basically steering a little bit of the main beam into invisible space, or out of the part of space that is visible for us to see. And when you do that, you get an increased directivity value, which is about 1.805 times the directivity of an ordinary Endfire. All of this stuff is going to be hard to keep in your head, and it is not really necessary for you to do so. I want you to be aware that these types of arrays exist, and I want you to be aware of the relationships between them in terms of which ones have more directivity, sort of the general shapes of their patterns and that kind of thing. But anytime you need to look something up, there are a lot of tables in chapter 6 in your books. In particular, tables 6.1 through 6.7 have lots of different performance parameters for a lot of different types of arrays, things like half power, beam width, and directivity, and the number of zeros or nulls in the pattern, the values of beta for different things, for the progressive phase shifts. All of that stuff you can look up in the tables in chapter 6. The reason I'm talking to you about this is to give you the high points so that you know when you go to look one of these things up what you're looking for. All right, the last topic for today is going to be 2D arrays. Simple conceptual explanation of how 2D arrays work. We've talked about uniform linear arrays. You can have a uniform linear array that's this way. We've also talked about the fact that if you convolve an antenna pattern or an antenna's physical currents by the grid of positions of elements on the array, then the resulting radiation pattern is a result of pattern multiplication between the element pattern and the array factor. So what happens if you convolve two arrays with each other? This would be like making a uniform linear array of uniform linear arrays. And what you get is a grid. So you can consider this to be an array of 4 arrays, like that. Or there's no reason why you couldn't consider it to be an array of 4 arrays horizontally too. I mean, that's fine. I don't care. So, by pattern multiplication, the total array factor for this thing is the array factor for this x-directed array multiplied by the array factor for that y-directed array, which is going to be equal to sine of, I'm going to name m the number of elements along x, m k dx is the spacing along x, divided by 2, sine theta cosine phi, that's the direction cosine along x, plus beta x, the progressive phase shift along x, all divided by the whole thing without m. So k dx over 2 sine theta cosine phi plus beta x. That's the array factor for the x-directed uniform linear array. So that needs to be multiplied by the same thing for the y-directed uniform linear array. So we're going to have n for the number of elements along y, k dy for the y spacing over 2 sine theta sine phi plus beta x. That's beta y now. Divided by sine of k dy over 2 sine theta sine phi plus beta y. So pattern multiplication not only tells you what happens when you take an antenna element, a single element, and put it in an array, it also tells you what happens when you make a grid out of a uniform linear array and how those sort of things interact with each other.